I have two equations up on the board right now, both of which represent the transmutation of something into something else. I'm going to number them 1 and 2. Can you tell me what kind of equation or what kind of reaction equation number 1 is? What kind of transmutation equation it is? Is it radioactivity? Is it nuclear fission? Or is it nuclear fusion? Or something else? Carrie? This would be fusion. Carrie, how do you know that it's a nuclear fusion? Good. It's two smaller nuclei becoming one bigger nucleus. Now, there's neutron involved here, there's energy involved here, and so on. But when determining what kind of reaction it is, we're looking for the elements themselves. We have two small things forming one heavy thing here. What's the second one? We've eliminated nuclear fusion now, so it's either going to be radioactivity or this is going to be nuclear fission. Jordan, what is it? Radioactivity or fission? How do you know? Good. One bigger nucleus is decaying into two smaller nuclei. And again, we've got even more neutrons this time and some energy and so on. We're not paying any attention to those in terms of determining what kind of reaction it is. They're important. Okay, we know from Friday they're really important because they're what help this thing to continue going on, and they also make sure that this equation balances out. But in the end, when determining what kind of reaction it is, we're not looking at that. We're just looking at the nuclei themselves. Okay, so let's take a closer look at nuclear fusion here. We know that nuclear fusion, these two positively charged hydrogen nuclei, small nuclei, but positively charged, want to fuse, well, they don't want to fuse together, actually. Okay, we try to fuse them together, or nature tries to fuse them together, but they don't want to fuse together. How come? What is it that wants to keep them apart, Jacob? Good. There's a repulsive force between these hydrogen nuclei. By Coulomb's law, the closer they get, the bigger the repulsive force, right? As R gets smaller and smaller and smaller, F gets bigger and bigger and bigger. They don't want to fuse together. We have to do something to cause them to fuse together. What is it that we got to do to cause them to fuse together? Or what is it that nature has to do to cause them to fuse together? We have to overcome that repulsive force. How? We have to use energy to overcome that repulsive force. So not only do we get energy out of this, but we have to pump energy into it to make these two nuclei fuse together. When we pump enough energy into it, which is usually, by the way, in the form of heat, usually, then these two nuclei can overcome the repulsive force, fuse together to form helium-3, an extra neutron, which is kind of just a byproduct of it, and some energy. More energy coming out of it than, of course, that we put into it. Let's take a look at the second reaction here. This is the fission reaction. Here we've got uranium-235, which is naturally radioactive. It'll undergo alpha decay, but it might take a long, long time to do that. We kind of kickstart it with a neutron. We fire a neutron at it. The neutron gets absorbed by uranium-235 and actually, for a brief moment, becomes uranium-236. Decaying into any one of a number of possible combinations. In the case that I have up on the board here, krypton-92, barium-141, and 3 neutrons. What is it that makes these 3 neutrons necessary here? Why do these three neutrons need to be here? Forget about what happens next. Okay, why are these neutrons necessary for this equation as I have it written, Nick? Not neutrons, but nucleons. Yeah, it's the law of conservation of nucleons. Perfect answer. Okay, we have to make sure that the atomic number, the charge balances out, right? It already does, but we also have to make sure the number of neutrons balances, neutrons and protons combined, or the nucleons balance out. We need neutrons in order to do that. In fact, we need 3 of them in order to do that. We get energy produced here as well. Now, this first reaction sustains itself by some of the energy that's produced here going into fusing more nuclei together. This one sustains itself in a completely different way, but still the products of the reaction will still lead to more reactions. So in the first one, it's the energy product causing more reactions. In this one, it's the neutron products causing more reactions. This is going to cause 3 more reactions. That is, assuming those neutrons can be absorbed by the uranium-235. It's going to produce 9 neutrons, which is going to cause 9 more reactions if they can all be absorbed. which produces 9 reactions and 27 neutrons, and so on and so on and so on. So this one grows pretty quickly because the energy causes more nuclei to fuse together, which produces more energy. And this one grows pretty quickly because the neutrons get absorbed by more uranium, causing more reactions, and it grows again exponentially pretty quickly here. All right, tell me where the energy comes from in both of these. How do we get energy out of a nuclear reaction, a fission or fusion reaction? There wasn't energy over here on the left side. How come there's energy on the right side? Stored? Yeah, kinda. Yeah, kinda. Remember we talked on Friday a little bit about Einstein energy, mass. We lose a little bit of mass in this process. We call it a mass defect. We'll talk a little bit more about that in just a couple minutes. But bottom line is we do lose a little bit of mass in this process. Mass disappears, but it's not destroyed. It's just converted to energy. And the energy that's released is that energy that comes from the missing mass. Remember we talked about ice and steam, two different forms of the same thing? Okay, we lose some ice. It's a warm day outside. We lose some ice. Well, now we got some steam. Well, it's not like it was destroyed. It was just changed into something else. On the right-hand side of the reaction, we have a bunch of steam that we didn't have before, but it came from the ice that we had on the left-hand side of the reaction. Okay, the energy on the right side comes from the mass that disappeared from the left side. Finally, one more question before we move on here. Tell me, two more questions actually. Tell me which of these two equations, nuclear fusion or nuclear fission, in itself, one single reaction, which one will produce more energy? Which one produces more energy here, Dallin? Nuclear fission produces more energy. Good. In a single reaction, the fission will produce more energy. Yes. What if I had 100 kilograms of hydrogen and I had 100 kilograms of uranium-235? In other words, I have equal mass of the parent nuclei in the first one as the parent nuclei in the second one. Okay, which one's going to produce more energy now? Okay, fusion, right. So fission releases more energy in a single reaction, but fusion will release more energy given the same amount of fuel, or per kilogram of fuel, fusion produces more energy. Good. I'm going to define a couple of terms now. One we addressed a little bit already. First one is mass defect. Second one, we haven't really talked about this one much at all. Now, there are a number of definitions for mass defect. All of them agree with each other. I'm going to give you two of them that are relevant to us. In the context of a single nucleus, okay, if I have uranium-235, there is what we call a mass defect. Or in the context of an entire reaction, okay, then we have what we call a mass defect. So there's a mass defect in a single nucleus. There's also a mass defect in a reaction. What does the mass defect mean in the context of a single nucleus? What's the difference in mass between the nucleus and the nucleons? That's weird. Okay, think about what that means. Think about what that means for a second. The nucleus and the things that make up the nucleus have a different mass. It's like saying there's 23 of us in this room right now, counting me. If we add up the mass of all of us, let's say all of us weighed 100 kilograms. That's a lot. Okay, we're not all that big, but let's say, just for ease of math, that we all weighed 100 kilograms. Okay, 23 times 100 is 2,300. What I'm saying here, though, is that we can add up the mass of all of us, which gives us 2,300 kilograms, yet the mass of all of us combined isn't 2,300 kilograms. It's more like 2,299. We each weigh 100 kilograms, but the total mass is only 2,299. It doesn't make sense. There's a difference in mass between the whole and the sum of the parts. The mass of the nucleus actually weighs a little bit less than the rest mass of all the nucleons, the thing that make up the nucleus. The difference comes down to an energy mass equivalence thing again. So it's not like it's as impossible as it sounds, because there is an energy thing in there as well. But the bottom line is, at least for now, we're going to say that the mass of the nucleus weighs a little bit less than the mass of what makes up the nucleus, which is weird. Then we define mass defect in terms of a fission or fusion reaction, which is what we were talking about just a minute ago. The difference in mass between the parent and daughter. What we end up with in a fission or fusion reaction ends up being a little bit less than what we started with in terms of mass. And again, the difference comes down to an energy thing. Right? If we lose a little bit of mass, well, now we got energy that we didn't have before because mass was converted to energy. Now another term, which we kind of alluded to, but we didn't call it by name, the binding energy. We're going to define this in two ways as well. A, in the context of the nucleus, of a single nucleus, and B, in the context of a reaction. In terms of a single nucleus, we call it the energy required to disassemble the nucleus. The energy required to rip the nucleus apart. And the second one, the second definition, this is in the context of a fission or fusion reaction, is the energy that gets released if binding energy is still available after the reaction. What does that really mean? What does this really mean in everyday language? The energy released in a reaction. How are we going to find that? Well, if we know the value of the mass defect, how much mass is lost in a reaction, the energy that's released in the reaction is going to be the mass defect times the speed of light squared. So we've got a nucleus that has a difference in mass between the nucleus and what makes up the nucleus and a corresponding energy. And then we have a reaction, fission, fusion, whatever, where we have a difference in mass between what we start with and what we end up with, and a corresponding energy that goes with that. If we have the mass defect in either case, we can find the binding energy in either case by using E is equal to mc squared. All right, this is going to become a little bit clearer in just a second here. Before I go on, though, I just want to identify two units that you're probably not familiar with. Okay, a U, first of all, is an atomic mass unit. These are both units of mass, by the way. A U is an atomic mass unit, and its value is on your data sheet. I believe it's 1.66 times 10 to the minus 27. Yes. Do you ever see an atomic mass unit? And odds are you will not, but if you ever do, then you know what it is. It's a unit of mass, 1.66 times 10 to the minus 27. If you want to convert it, just do the ratio thing. One atomic mass unit is equal to 1.66 times 10 to the minus 27 kilograms equals 27 atomic mass units, or whatever it happens to be, over X. Solve for the number of kilograms, right? Now the second one, this is a little bit more confusing, but it's a unit of mass as well, a mega electron volt per c squared. Nowhere on your data sheet does it give you a nice clear conversion from mega electron volts to kilograms. So what I want to do is teach you a nice little trick to do the conversion. Everybody look at your data sheet right now. Everybody take out your data sheet right now. If you don't have one, you don't know where yours is, grab one from the front of the room. I want everybody to be looking at it right now. In the top right-hand corner of your data sheet, it says an electron has a mass of 9.11 times 10 to the minus 31 kilograms. Down below, under the heading of first generation fermions, you don't even know what a fermion is yet. You won't until Wednesday or Thursday of this week. You see an electron again. It says its mass is 0.511 mega electron volts per c squared. Well, we know that the electron weighs the same as an electron because it's the same thing. So the conversion factor that we're going to do for this is it's the same idea as we did right here, except it's not as clearly written out on your data sheet. We're going to say 0.511 times 10 to the 6 electron volts per c squared, because that's what it says an electron volt is, right? Or sorry, an electron is 0.511 mega electron volts per c squared. I just converted it to electron volts per c squared. So that's what it tells me the mass of an electron is in the bottom right-hand corner of your page. In the top right-hand corner, it tells me an electron is 9.11 times 10 to the minus 31 kilograms. So if you end up with 16 electron volts or mega electron volts per c squared, then you would say 16 times 10 to the 6 electron volts per c squared over x kilograms in sulfur kilograms. I would be surprised if on a test you actually have to use either one of these, but we're responsible for them. So if you see them, I want you to be able to do the conversion. Okay, bottom line is you always want to work in kilograms. So if you've got mega electron volts per c squared or giga electron volts per c squared, all you do for giga electron volts is say 16 times 10 to the, if you were given giga electron volts per c squared, 16 times 10 to the 9 electron volts per c squared, right? Because giga is 10 to the 9. And then solve for x in both cases. All right, now that we know those units of mass, I want to do an equation, or a problem, I should say, involving the energy released by a fission reaction. This is exactly the fission reaction that I gave you as an example, probably because it's certainly one of the most common ones out there. Calculate the energy released by the fission reaction shown on the board here. Where would we even start? Well, what do we know about this? Okay, what do we know about this? We know that if there's energy released by this reaction, we call it binding energy, right? That binding energy corresponds to mass missing, the missing mass, the mass defect. We know that there's going to be more mass here than there is here. We're going to say the mass of the parent is greater than the mass of the daughter nuclei. If we can find the mass of the parent nuclei and the mass of the daughter nuclei and the difference between the two, then we can find the energy that's released in the reaction by just multiplying that number by c squared. So let's do that now. Let's get the mass defect, which comes from getting the mass of each of the parents in each of the daughter nuclei. On the table that I just flipped by there, and on the table that's photocopied in your notes, it gives you mass of all these different nuclei in atomic mass units. If you get a question like this on a test, I would expect that it would be given to you in kilograms, which is going to make it a little bit easier. But we're doing it the harder way just in case. Okay, we're given the mass of uranium-235 in atomic mass units. Take a look at that. Uranium-235, bottom right-hand corner of this table. It tells us that it's 235.043930 atomic mass units. In a neutron, it tells me in the top right-hand corner that the mass of a neutron is 1.008665 atomic mass units. So if we add those up, then we're going to get the mass of our product, or sorry, of our parent. Now let's go to the right-hand side. The mass of the daughter nuclei, barium-141, is 140 from that table, 0.914412. Again, I think if you get this on a test, it'll be given to you in kilograms, not atomic mass units, but that's okay. It just makes it easier. Krypton-92. Krypton-92 has an atomic mass of 91.926156, and 3 neutrons give me 3 times 1.008665 atomic mass units. This side of the room, Caitlin and Over, you guys are responsible for finding the mass of the parent nuclei, the blue ones. In this side of the room, Merrick Over, you guys are responsible for finding the mass of the daughter nuclei. Those are the green ones. Who's got a number for the left-hand side, the mass of the parent, the blue one here? Dylan, what do you got there? Terry, what do you got? Sorry, I made a mistake there. Sorry, 236 point. Thank you. Okay, there's the total mass of the parent. Okay, somebody on this side of the room, what do we get for the daughter nuclei in there, Merrick? 66563. Thank you. Notice the mass of the parent is slightly bigger than the mass of the daughter. Not much, right, but a little bit. Hey, by the way, why didn't I do this in kilograms? I got to convert to kilograms at some point. I might as well do it now, though, as opposed to at the beginning. Because if I do it at the beginning, then I've got to... Is this one off? This one's off? If I convert it to kilograms in the beginning, then I've got to convert all of them to kilograms, right? If I do it at the end, then all I have to do is convert one number to kilograms. Carrie, what do you end up getting there? 0.52595. Okay, thank you. Still bigger than the daughter nuclei, though, right? All right, let's get the mass defect now. That's going to be the difference between the two of them, right? 236.052595 minus 235.8666563. Everybody's going to do that one. Dylan, what do we get for the mass defect? 6032. Thank you. That's a small number, right? We would expect it to be. We're not going to lose very much mass in this reaction, right? Okay, that seems reasonable. Now we got to convert that to kilograms. So let's say one atomic mass unit that's equal to 1.66 times 10 to the minus 27 kilograms. We know this because it says it on our data sheet, right? Just a couple slides ago, I showed you how to do that conversion. One atomic mass unit is 1.66. 0.186032 atomic mass units is X kilograms. Let's get the mass defect in kilograms. Everybody find that one too, please. What is it there, Hannah? You're so fast there. 3.0828. Okay. 28. Thank you. So we lose in this one particular reaction 3.0881312 times 10 to the minus 28 kilograms. Now, where do you think you're going to get the energy from? The binding energy? We know this, right? Where's the energy going to come from? How are we going to find the energy from that mass? Grant? Sure we know, guys. Listen, we know this. Just give it some thought here, guys. We have the mass defect. We have how much mass was lost in the process. Mitchell, where's the energy going to come from? Good. Equals mc squared. And we're going to say 3.0881312 times 10 to the minus 28 kilograms. Now, this is where you want to be in kilograms. If you're given the numbers in kilograms already, you just save this step. That's all, right? You don't have to do this. But you got to get into kilograms if you're not already. Multiply that by 3 times 10 to the 8. Square it. Don't forget to square it. And when you do, you get your energy. What units would this energy be in? It's going to be joules, electron volts, mega electron volts. What is it? Mark, what's it going to be in? It's going to be in joules, right? If the answers, it's multiple choice and your answers are all in electron volts, then convert it. Convert it to electron volts. Yeah, but we get joules when we're using kilograms and meters per second and so on. So when you get a question where you're looking for the energy that's released or the binding energy, you need the energy that's lost in the reaction. Take the mass of the reactants, the mass of the product, subtract the two, and then use equals mc squared. Or if you're looking for the mass defect in a particular nucleus, not a reaction, but just a single nucleus, then get the difference in mass between the nucleus and what makes up the nucleus, the nucleons. And then, once you get that mass defect, multiply by c squared and get the energy that's released. I'm going to refer you to page 819 and ask you to work on these 3 questions, please, for homework for tomorrow.